What I'm going to present to you now, and is this working okay? You can all hear me? Okay, what I'm going to present to you now is the developments of the variation management framework. I'll give you a little introduction to what it was to begin with when we started this program, and then I just need to give you this introduction because this is going to be the topic of the workshop after lunch. The typical example I give for the variation management framework is a very simple design task to decide how much force we need to ensure to press on the lid of perhaps an injection device. And this can be modeled through a transfer function, so we can see the press-on force will be determined in newtons perhaps, and we'll have a target specification, and based on the design we'll have this transfer function leading to a nominal target for the diameter of the lid. But in production we'd expect the diameter to change, and as a consequence the variation will transfer into the press-on force. Now when you produce a robust design, as we know, what we actually do is have the same ingoing variation here and resulting in a much tighter performance output here. Of course we can go the other way around, which is often the case. We stick with the same performance but slacken the tolerances we pass down to production. And this gradient at this point, at the nominal base, is a metric, or we call theta, for the sensitivity. Now this is just the design aspect, so this is linking design parameters to functional parameters. But we also may say, well, is it really necessary to go into such detail in our robustness optimization and our tolerance tightening if we've chosen this value at random? Of course it needs to have some research behind it, which is exactly where Emily's presentation in the perceived quality comes in. We need to fit these target values to some real data, and we need to fit the limits to some real data. So we have a quadrant to the other side of the engineering design, which is the perceived quality quadrant. And there we'll have some kind of quality loss curve. So as we vary from the point of max perceived quality, we will have a customer satisfaction reduction. So really the nominal value should coincide with the point of minimum quality loss. We can then track this in the other direction, so we can say, well, we need to achieve a certain value for our design parameters. Then we have a sensitivity of our production process parameters in order to achieve them. So this is another element of robustness here, where variation in our PP level leads to variation in our DP level, leads to variation in our product performance, which eventually leads to variation in the customer satisfaction. So this is a very simple framework where we can link these different domains of variation together towards one common goal of increasing the customer satisfaction. Now, as I say, this is coming in a forthcoming production, but about 2 weeks ago, we also found a diagram in Dan Whitney's book in 2004, which is remarkably similar to this, describing the cost-risk management process. Now we've used it to position our research outputs. We've also used it to position the different levers available for us. So when we want to have some kind of mitigating step in order to improve quality, there are basically, as we've defined it, only 7 levers available to you to improve quality. And these are at these 7 blue points. In addition, in a recent publication published earlier this year, we published the 15 principles of robust design. And those 15 principles can be mapped into this quadrant here, either in lever 2, lever 3, or lever 4. So now we have a very good framework where we can put down all of the levers and principles available to us to improve quality. And it doesn't matter whether you're in the perceived quality domain, the engineering design domain, or production, we're all focusing on the same thing. We've also used it to position our PhDs in our major research project, so each one is working on a different area. And we've used the basic outline of the framework to describe the robust design and product development process. leading from the customer, defining objective market requirements, a concept selection, an engineering specification, through the engineering design process to the design freeze where we have our part dimensions and tolerances, and then down to the tool design and verification process until we get the start of production. Now, if we try and use this basic framework to identify or describe what our objectives are as an organization, we can think of it in the design terms, in this one here. We may start out wanting to achieve quite a specific or tight customer satisfaction band. We want the customers to basically have the same and high quality experience. The goal of the people working in this quadrant is to try and pass on as big a tolerance window as possible for the functional specification. So this is all what Emily was proposing. We may have specific requirements which are key characteristics we want to keep, but the rest we want to give as big a band as possible for the engineering designers to meet. Furthermore, we want as few functional requirements as possible to be passed over. So this department really does have an impact and a responsibility towards quality. And of course, in the engineering design domain, we want to change that functional performance window into an even broader window for production to have to meet. So the better designers we are, the bigger tolerance window we're passing down to production. And of course, production are becoming extremely robust when they're able to allow their process parameters to vary and still achieve the required dimensions in their parts. Now, once we've decided and we fix the drawing, we start up production, the idea is we flip it over and we're trying to minimize the amount of variation and pass as much variation down to achieve a tighter quality band as possible to the customer. So we can just use these to define the quality objectives of an organization on a very high level. So what we've noticed is just over the last 3 years when using this as a communication document, many people are now talking to me and explaining where they are positioned, in which quadrant they're working. We talk about robustness over these frameworks. It's a very good educational tool, and my students, when they're going through the Robust Design course, find it very useful. But as an operational tool, it's pretty hopeless. I mean, we don't have designs with one function requirement to one design parameter to one process parameter. The big problem is we've got lots of them and they're all interlinked. So can we make it an operational tool? Well, these are paraphrased quotes from discussions of people we've been working with, and I was hoping that the majority of these would be here in the room to verify. But Novo Nordisk have done a lot of work on the design clarity side and looking at ensuring good kinematics, but they expressed that there can be sometimes an issue maintaining a complete functional overview between which design parameters affect which functions, basically related to change management. When we were talking to Jaguar Land Rover, they were actually saying the biggest concern for them was not really knowing the perceived quality elements on how much variation is actually perceived as a quality issue by the customer. So they were talking about this first quadrant being an issue. In recent collaboration started up with Radiometer, they were saying that they've modeled many, many different transfer functions, but having a good framework to link all of these transfer functions and the variation together is not there at the moment in theory or practice. Please bear in mind, these are paraphrased quotes. You can verify it with the person himself afterwards. And when we had a keynote speech a couple of years ago from LEGO, they were talking about the need for shared KPIs across production, design, and marketing. So one of the ways LEGO achieves their quality is by production and design having a shared KPI, getting the organization to face the same direction. Now, I think I'll go into what you said after the break in the intro to the workshop, but you also gave some very interesting feedback in your survey talking about the problems that you encounter in your organizations related to quality. Those questions we gave you were what we believe our VMF tool and method solves. So let's move on to it. How can we turn the VMF into an operational tool? Well, the first thing we need to do is increase the number of design parameters and function requirements. It's not a one-to-one relationship. It's very mixed. And when we have a number of function requirements related to a number of design parameters, we will also have not a one-to-one relation, but we may have some coupled relations. So in this case, this design parameter is affecting two function requirements, and we can begin to capture that in one of these matrices. Seems possible, but can we really do this type of thing in reality? Well, we thought, well, let's give it a go and see what problems we encounter. We took a simple product. Well, it seems simple on the face of it. It's called the PenMate. And this is basically an add-on device to injection devices as a way of hiding the needle for someone doing an injection for people who have needle phobia. So they basically load the device into the PenMate, put it against their skin, push the button, and it fires the injection in. Fires probably isn't the right marketing term there. Now, when we tried to map this as a case study, we didn't start at the perceived quality loss, but we said, let's map the perceived quality loss onto a number of objective market requirements. Those objective market requirements are then transferred up to a number of functional requirements which are in the specification document. But we also thought, well, we probably haven't got time to investigate into all of the function requirements, so let's just take the key characteristics, what's important. So we just took the 4 key characteristic function requirements, and we managed with some fairly simple weightings, rudimentary sensitivity analysis to put some sensitivity values of these functions relative to these market requirements. We then looked at the part design and mapped on the design parameters, which are the design parameters here, of each of the components relative to how they affect the functions. And we can see that there is actually quite a lot of overlap. And it's interesting working with these companies like Novo Nordisk and things like the PenMate, because there is such a small design envelope, you have to cram more and more functionality into fewer and fewer parts, which makes it a really, really interesting design challenge, and you have to manage quite a lot of these couplings in this area. And then based on some basic process capability data, but some assumptions as well, we could do some estimations of what the sensitivity of the design parameters are to the different process parameters. So it actually wasn't, we didn't really come up with anything that problematic in creating a complete VMF for this case. Now, what you have when you do this is a link between the perceived quality to the customer through to the function requirements, through to all the design parameters that affect those function requirements, and through to all the process parameters that affect those design parameters. So this is a very good way of making the whole organization face in the same direction. Production now no longer necessarily need to only maintain their PPs to achieve their DPs, but they can start adjusting these in order to achieve the customer satisfaction and the functional performance of the product. Now, I'm guessing what you're probably thinking right now, and it's either, that's pretty neat, surprised that hasn't been tried before, or possibly more likely, as this is a room of engineers, that looks like a more complicated QFD. We hate doing QFD, so that's not going to work. And one of your justifications could be, we have so many design parameters in our design. We have thousands, maybe getting on towards tens or hundreds of thousands of design parameters. Are you really going to be able to map that in a matrix that looks like that? It's ridiculous. You may be thinking the information for filling in all those cells is just not available. It's just going to be a completely sparse, empty matrix when we do this. Or you may be thinking, our design iteration cycles occur quite quickly. So the minute we've thrown in all this data into a matrix like this, we've changed the design, and therefore we have to throw that whole matrix in the bin and redo it. So it's just not going to be agile enough to keep up with the pace of design change. Hands up if you were in the ors compared to the ethers. Okay. So I'm going to do my best for the last bit of this presentation and the workshop to convince you that maybe we can overcome these ors. But of course, we're in research. This is what it's all about. So if we ask, we've got too many design parameters in our design. Well, when we're doing kinematic design, you can cope with it quite easily. You can club design parameters together within components. You can club components together within bodies. You can lump them, you can have analyses on dimension levels with parts, subsystems, even assemblies. And it all works at different scales. So I think we've got complete modularization here. So we can start off a process where perhaps we don't look at design parameters, we're just looking at interfaces between parts to achieve functions. Then we can go a step deeper and say, okay, well, which of these are really important? Let's break down into the design parameters here and put an extra layer on. But the point is we can have it at the appropriate layer of abstraction for our current stage of design. Is the information available? Well, I think this is one of the main motivations. I mean, if you look at PLM systems at the moment, they are not really well supporting us in quality and robustness management, in that the management system is at the wrong level of abstraction. We create all of these simulations across our companies. We have CAT simulations, finite element analysis, fluid dynamics, we have mold flow simulations, we have DOEs, we have process capability databases, we have user studies. Where do we bring all of this data that's already available together into one framework so we can see how it all relates to each other? I don't think we have that at the moment. But we certainly don't necessarily have to say, you need to do more simulations and need to fill in all of these boxes. It's just what we have, we can place relative to each other. And the information that we don't have should be as interesting and relevant to you as anything else. Should these squares be blank? Is it okay? Or is it a problem that we do not have a sensitivity value for this particular cell? Is it a problem to our organization and a risk that we don't know the sensitivity of that function to that design parameter? When there's a blank cell, we have the opportunity to allocate simulation resources. And finally, and probably the most tricky one, the design keeps changing and the matrix is not agile enough. Well, it's very common practice that we start out with a design specification. A product specification. These are all the functional requirements. They can go straight into the vertical axes. So there's not a problem there, and we can easily pull out some indicators from that. Then if we look at the link between the functional requirements and the part relations, well, we can fill that in the matrix, and we can get some very useful insights at this level. So it's not just recording for recording's sake, but when you map these relations, you learn a lot. This is the relation maps between parts and function requirements in one of the injection devices we are working with. And we can see that on a single component, how many functions interact with it and which surfaces. And we can produce a very simple relational matrix here. Now, we don't need to map sensitivity values or any complicated maths here. This is just geometry and our design intent. And we can actually say, when we look at the function requirements listed here, so the matrix is inverted, we can say which of the function requirements are the most coupled to numerous design parameters. So we can say, is that a problem? This is a critical functional requirement, and it seems to be dependent on numerous design parameters. We can also say which components are linked to the most functions, and we can identify critical components and then the sequence in which we want to set the dimensions and tolerances for each of the components. But this is useful and interesting data just at this simple level. And it's not really asking us to do any more. Then, okay, so going a step beyond just a relational database, a relational matrix, which is basically this level, we may have a few question marks here, which might also be interesting at this stage of analysis. Not just relations, but we can identify here that there are a number of functional couplings. So in our design that we've produced, compared to another design, we have 1, 2, 3, possibly 4, possibly 5 different functional couplings within this concept. So we now have 5 couplings. We can compare it to another design which maybe has 2 or 3. It's an indicator to say how difficult this design is going to be. Not only the couplings, we can look at the direction in which the couplings work. So this coupling, the design parameter changes the function requirement in the same direction as it does in this one, but in this design parameter, it changes them in opposite directions. So this design parameter is going to cause us more of an issue. This is more of a trade-off point than any other. Again, no complicated maths, it's just communicating design intent. Now maybe we allocate our first few simulations. So we've got our first few sensitivity values. Is this useful or is it a waste of time? Well, I would say it's very useful to know that this design parameter is, infinitely more sensitive than these compared to this function requirement. Some of these, just on their own, can be good drivers for design development. And then, of course, when we start filling in the matrix more and more, we can start defining the nominal dimensions and the tolerance windows and stating where our tolerances we're unsure of due to unfilled out sensitivities. So we can leave placeholders as places where we're not quite yet certain of. I think I'm going to have to wrap up now, and we'll move on till after the break. Okay. We'll come back to that at the introduction to the workshop. But one small point, the thing that you'll see is a first version demonstrator of the software. In this case, the front end is the same as the back end. So it's basically a matrix and Excel spreadsheet. In the demonstrator that will come out at the end of the year, the matrix that you'll see is just the front end of the software. It's just a viewpoint. Where you actually enter the data in is into a tree structure in the background of the database. And it will be driven by transfer functions and surrogate models rather than single sensitivity values. And there's a few good reasons for doing this. We're running a number of cases at the moment. We've done the PenMate case. You have the Valvewood wind reader case coming up. And we're running a couple of cases with radiometer right now. In a closing statement, we as the Robust Design Group believe that the VMF can be created not just for mechanical products, but for any product. We believe it can be useful and beneficial at every stage of development. And we really think that when it's implemented properly, it will point all members of an organization who have an impact on quality facing the same direction with a common template to discuss it. I think everyone's hungry for lunch, but I'm happy to field 1 or 2 questions if you have it, and I'll try to be quick. Are there any questions?
How do you deal with interactions between the parameters, and is it relevant at all in this case?
That's a very good question, and it's in a couple of the slides I slipped over, but the interactions between the design parameters are not modeled in the current version of the VMF. So every sensitivity value is independent. But it's not very difficult with the relational database when we can model the covariances with a Monte Carlo simulation to show how the sensitivities of each update relative to a change in another parameter. So we will integrate it, and it can be done, but in the demonstrator you'll be working in, it's not relevant.